So in previous chapter 4 and 5, we have learned about the amplitude modulation, transmission as well as reception. So for this chapter, we're going to continue to learn about another communication system in AM signal. Okay, so the objectives of this chapter, all right, in this chapter you will learn about the type of SSB system and how to generate the single sideband signals, as well as the electronic components that we can use to develop the SSB transmitters or receivers. So before that, I would like to explain to you about two types of communication system. One is what we call as baseband communication. So this baseband communication, basically it doesn't have the process of shifting the frequency, and mostly it can be done by using wired transmission. Either you use the twisted cable, coax cable, or fiber optic cable. And this type of communication system will have a signal that very high energy and use low frequency. And most of the application for this communication system is not suitable for application that use radio frequency, such as in radio communication, microwave, or satellite communication. Another one more communication system is what we call carrier communication. So this is what you learn all this one about AM. So the carrier communication uses a technique in modulating the frequency or amplitude, but most of the time in this carrier communication we modulate and shift the frequency of the carrier signal. So this type of carrier communication is very suitable for application that uses radio frequency as transmission medium, such as in radio communication, microwave, and satellite communication. So what are the type of single sideband system that mostly used in any application? So there are 5 here type of SSB system, and we will learn and see one by one the differences between this system. So the first time is the AM SSB full carrier. All right, when we read the name, of course it will use full energy or full power of carrier signal. Second is SSB suppressed carrier. Basically this one, we don't want to transmit the power or energy of the carrier signal inside the AM signal. The third one is the AM SSB reduced carrier. So this type of signal has carrier signal but with very low energy. The fourth one is the AM independent sideband, and lastly the AM vestigial sideband. So on the next slide, we will see the differences between these SSB systems according to the frequency spectrum. Okay, so for the first one, the DSBFC double sideband full carrier. So this is the one that we have learned in chapter 4. All right. So for the double sideband full carrier, so it has double sideband USB and LSB, as well as full energy on the carrier signal. Okay. But for the SSB full carrier, it just only one side of sideband, either upper or lower for this spectrum. It shows only on the upper side, and also the full energy on the carrier signal. And for the SSB suppressed carrier, it also has one side of sideband, but without any energy of the carrier signal. Okay, so the carrier power here is 0. The next one is SSB RC reduced carrier. It also has one side of sideband and very low energy on the carrier signal. Right. For the independent sideband, all right, it actually has, if you see in the spectrum here, it has two sidebands, but these sidebands actually is not related to each other. Because why? That is why the on the low side band it shows as a carrier channel A. For the upper side it shows as channel B. So this channel A and channel B might be not related to each other, all right, and it has very low energy on the carrier signal. Okay, so on the vestigial SB, all right, for this one, it also has both side of sideband, lower and upper side, and it also has quite very high power on the carrier. But for the lower side and upper side band, um, basically it's a different range or band on the upper side and lower side. So if you see over here, the length of the frequency range on the upper side is longer than the one in the lower side. So in this vestigial SB, basically it's actually will transmit the carrier signal together with one of the sideband. All right, and for the lower frequency on the modulating signal, it will transmit as double sideband. But if it use higher frequency on the modulating signal, it will transmit as SSB. So for the vestigial SB here, it can be either DSB or SSB depending on the frequency of modulating signal. Okay, so for the, I forgot to tell, the independent SB over here, basically it can be like a double sideband, but with two SSB SC. So if you see the SSB SC up here, you will get either like two SSBSC in the independent sideband, but with different sidebands, either it's lower or upper. Okay, I hope you can understand the differences between this type of single sidebands. But of course, the most common system in the single sideband are these three. Okay, so as a recap, we want to remember or revise again how we can calculate the power of each components in the frequency spectrum. So for the carrier, if you go back to the slide, actually on this slide is already given how we can find the power of each part or if each element, like carrier power carrier of the power of the carrier over here, you can take the voltage or the amplitude of carrier, okay, and then power of 2 divided by the resistance. All right, and for the sidebands you can take the modulation index M times with power of 2 times with power of carrier and divide by 4. Okay, so that will be how we can try to find the power of each part. So I will try to write again over here, so you can have the amplitude of carrier with power of 2 divided by R. For LSB over here, or one part of the sideband, you can take the modulation index power of 2 times with the power of carrier divided by 4 R resistance. Okay, so for only for one sideband. So using this information, I hope you know how to find the power of each element in the frequency spectrum. Okay, what are the problems that double sideband has that would be an advantage for the single sideband? So for double sideband, as you know, or maybe later on you try to calculate the total power of a double sideband, it's actually used much more power to compare with the single sideband logically. Okay, and uh, if you read here, the power of the carrier basically has two-third of the total power. Okay, and of course, large bandwidth is utilized. If you take the highest frequency minus with the lowest frequency in the spectrum, in the frequency spectrum, you will see that double sideband system has a larger bandwidth compared to the single sideband system. So the SBSP or double sideband full carrier basically is not efficient when we compare to the power as well as the bandwidth. Okay, so this will be the frequency spectrum of the single sideband full carrier, whereby it has the carrier as well as one sideband over here. So for this, it can be either one. If you want to have the lower sideband, so the upper sideband will be not on the spectrum. But for this light, okay, it shows that it has upper side band, so we don't have the lower side band. So the carrier power as well as the sideband, you will use the same equation that I explained earlier. So for this one, you can take the amplitude of the carrier power of 2 divided by R, and for the sideband over here, you can use the modulation index power of 2 and power times with the carrier power divided by 4R. So if you calculate the total power of this single sideband system, you will get lower power when you compare to double sideband with the same full carrier system. Okay, so so single sideband system, if you read over here, it's still the carrier still can be transmitted at a full power, okay, but only with the one of the sideband, and it requires less bandwidth compared to double sideband full carrier, but still it can produce a modulated signal with a lower amplitude. Okay, so for the suppressed carrier on the spectrum, basically we won't see any we call it carrier signal or carrier spectrum, and only will have one side of one side of the sideband. Okay, either lower or upper. And if you calculate the total power of the SSB suppressed carrier, of course it will be lower than SSB full carrier, because we don't calculate or include the power of carrier signal. Only take the power of the sideband, one of the sideband. Okay, so for this one, the carrier is totally suppressed or eliminated, and only one of the sideband will be seen on the frequency spectrum. All right, so that's why, or therefore, SSBSC suppressed carrier requires less bandwidth compared to the DSB system, as well as SSB full carrier system. Okay. Right. So this is the shape of waveform or the envelope of the SSB full carrier. All right, a little bit different with the double sideband envelope that we have learned and see in the chapter 4. So for the SSB-FC, all right, it still look like an envelope, but maybe a little bit different, because why? We will only get the maximum and minimum peak on the waveform to be slightly smaller than the envelope in the double sideband system. So for the maximum peak over here, you will get when you try to add the amplitude of the carrier with the amplitude of the upper sideband. And for the minimum peak on the envelope, you will take the carrier amplitude minus with the amplitude of sideband. Okay. So for the single sideband suppressed carrier, since the carrier has been eliminated, on the spectrum or on the system. Okay, so you will see that the output of SSB suppressed carrier will be just a simple sine wave shape. Okay, so the power, sorry, the amplitude of the signal will be the amplitude of the sideband itself, right? So if you see over here, this SSB suppressed carrier waveform doesn't has or doesn't give the shape of envelope for this system. Not like this or maybe double sideband system that we have learned in chapter 4. So a little bit different for the SSB suppressed carrier. So these are the comparison in the term of waveform or envelopes shape depending on the system that we choose. All right, for this one is the envelope that we have learned in chapter 4, double sideband full carrier. All right, and for this one is double sideband suppressed carrier, whereby we can see the meeting of the on the zero axis. All right, and then for the single sideband suppressed carrier, we only will get a very simple sine wave on the waveform. Okay, so that's it for this part of the video. I will continue this chapter on the next video. Thank you.